Hi everybody. In the previous discussions we have examined how to use Kepler's third law both in ratio form for multiple objects orbiting around the same body, as well as the Newtonian version of Kepler's third law where we combined Newton's law of universal gravitation with the equation for centripetal force, with centripetal force being mass times centripetal acceleration, and using the a sub c equals 4 pi squared r over t squared version of centripetal acceleration. And from that, we got the equation period squared equals 4 pi squared r cubed over big G times m, where m is the mass of the object being orbited, and big G is Newton's universal gravitational constant. In this video, we are going to look at situations involving using the ratio form of it, except in a special situation. We're going to say, okay, how can we determine a relationship for objects orbiting stars outside of our solar system, or for that matter, any object? So here's what we're going to do. Something to be kept in mind is that since most stars, actually about 2/3 of the stars in our Milky Way galaxy, exist in multiple star systems, it's often possible to analyze the orbits of stars to determine the masses of the individual stars. Now, it's harder to do this with our sun because our sun isn't being orbited by other stars or anything like that. Our sun's kind of special. But our sun is being orbited by 8 planets, a bunch of dwarf planets, and a whole bunch of other things. So we know the characteristics of our sun quite well. But we can extend from this characteristics of other stars. So this is useful in a variety of circumstances, particularly in exobiology, because knowing the mass and temperature of a star allows scientists to determine whether there are any planets in that star's habitable zone where liquid water could potentially exist on the surface and maybe be conducive to the evolution of life. We call these potentially habitable exoplanets. So the hard way of determining the mass of a star involves using the full equation t squared equals 4 pi squared r cubed over gm and solve for the mass of the star by plugging in all the items in SI units. But a lot of times scientists find it a lot easier to use a ratio version of this. So we start from the initial equation and turn this into a ratio equation, first by turning it into a proportionality and saying, hey, period squared is proportional to r cubed over m, where r is the average orbital distance, i.e. the semi-major axis, often called lowercase a. I go back and forth between them so that you know that the same thing has two different symbols, lowercase r and lowercase a, just depending on the mood of the person writing the equation. And m is the mass of the central object being orbited. Well, here's the thing. I can turn this into a ratio, as you can with any proportionality, and the proportionality sign becomes an equal sign when you turn it into a ratio. And in particular, I'm going to use the fact that there is one particular planet that I know everything about. I know that it takes Earth 1 year to orbit our sun once, at an orbital distance of 1 astronomical unit. That's almost the definition of the astronomical unit, Earth's average distance from the sun. And what is the mass of our sun? Well, the mass of our sun is 1 solar mass. So what I can do is I can say, okay, orbital period squared in years is equal to orbital distance in astronomical units cubed divided by the mass of the object being orbited in solar masses. So with that in mind, let's look at a couple of examples. Let's consider a planet that takes 5.4 years to orbit around a star whose mass happens to be known by some other means, maybe spectral analysis, to be 0.752 times the mass of our sun. Well, spectral analysis wouldn't get it to you that precise, but anyway, maybe we already found another planet around that star. So calculate how far the planet orbits from its star. All right, well, write our givens. Orbital period is known, the mass of the star is known. And notice that our units are years and solar masses, not SI units, because we're going to use that ratio form of the equation with the special units. Period squared in years is equal to orbital radius in AUs cubed divided by mass in solar masses. And we want the orbital radius, r. Well, isolate the equation for r, so multiply both sides by mass in solar masses, we get r cubed, and then take the cube root of both sides. And now that we've done that, we're ready to plug in our numbers. Notice that when we plug them in, they don't have units because what is this symbol? This is the mass in solar masses. Well, the mass is 0.752 solar masses, so therefore the mass in solar masses is just 0.752. Orbital period in years, well, 5.40. And don't forget to square that. And when you multiply that out and take the cube root, you get that the orbital radius in this case is 2.80 astronomical units. Okay, all well and good. How about something that's kind of useful? In this example, we're asked to find the mass of a star. So there's a planet called Kepler 1649c. It's actually a potentially habitable extrasolar planet orbiting around the star Kepler 1649 at a distance of 0.0649 AUs. This is actually a real planet that scientists have found and confirmed in around April of 2020. So if the orbital period of this planet is 19.535 days, calculate the mass of the star. So again, we'll show our givens. So the orbital radius is known. Notice that the orbital period needed to be converted because the formula that we're using requires the orbital period to be in years. So, with that in mind, we have Kepler's third law in this ratio form and involving orbital periods in years, orbital distances in AUs, and central object masses in solar masses. So we solve for the mass, and multiply both sides by m, divide both sides by t squared, and then we plug in the numbers. It's that simple. And then we get a mass of 0.0956 solar masses. So actually this star is much less massive than our sun. It's less than 1/10 of our sun's mass. But this being an artist's conception of what a view might look like from this planet's surface, one of the results of having such a small mass is that the star actually burns through its nuclear fuel very slowly. So our sun is about 4.5 billion years old, and it's going to last for about another 5.5 billion years before it becomes a red giant and does all that stuff, and Earth won't be habitable anymore. But this star will actually last for about 1 trillion years. So if this planet is indeed habitable, it could be habitable for a very long time. So potentially exciting. But yeah, that's how scientists can determine the mass of stars, just by watching things that orbit them and figuring out the orbital parameters. So I hope that was informative and a good illustration of how to use Kepler's third law in kind of more advanced ratio form to figure out masses of central stars, or knowing masses, figure out other orbital parameters. So hope to see you all next time when we begin talking about the conservation of energy. Have a good one.